share my screen. Okay, so this is a presentation that is ST05, supervised learning and linear discriminant analysis. And we're going to start. This is the first method we're going to look at. This method has been around for a long time, and it is parametric in a sense, although there's a variation of the method that assumes that does not assume a particular distribution. But we'll focus now on this one, which has several limitations. It works in some cases, but it has some limitations, as we will be seeing now. We saw earlier that there are two classes of supervised learning, what we call regression. Okay, that's when your response variable. Pardon me?
I have trouble with my internet, so I don't listen clearly. The quiz are going to be at the end of the class?
Yeah, 12 o'clock.
Okay. And why we are not gonna do it right now?
Because what's happened, I remember that the last time I did it at the beginning of the class, then we lost a lot of time. And at the end, people started taking more time than needed. And you're so excited when you finish the test that you don't want to have class. Okay.
Okay.
So, but this material that I'm going to talk about now is not going to be included in the exam. Okay.
Thank you, teacher.
Okay.
Teacher, how much time does the exam is going to last?
45 minutes.
5
45
minutes?
45.
45.
45
Okay,
minutes.
okay.
Now,
Thank
if when we start the exam, if some of you finish earlier, you can leave earlier. The exam is actually can be solved in much less than 45 minutes. Okay. It's a very simple quiz.
And teacher?
Yeah.
What is the name of the presentation?
It's ST_05, AM05, sorry, AM05 classification and linear discriminant analysis.
Thank you.
Oh, you're welcome. You're welcome. Let me move this bar here.
Teacher,
Yeah.
is there any chance we can do the test right now?
I'd rather have it at the end.
Okay.
It works better. It works better for you also. Okay, so you don't have to be thinking about the exam once we have the class. Okay. We'll try. Next time we will try it differently. We'll experiment with this. Okay. Okay, so we talked about supervised learning. We saw that there were essentially two methods of supervised learning, regression and classification. We saw that regression is when you have the response or that you are trying to predict is a continuous variable, such as income, sales, and so on. Okay. The input variables or the predictors can be anything, can be continuous, can be discrete, it doesn't matter. In classification, the response or target variable is categorical, okay? So we're trying to predict based on some predictors, which also can be continuous in general, not for every method, but in general can be continuous, can be categorical, it doesn't matter what they are, but we want to be able to predict a response, which is a category belonging to a category, depending on the various values of the independent or predictor variables. Okay. Now, we're going to be focusing now in classification. In classification, we'll focus in several methods. The first method that we're going to discuss has some restrictions. And that is that the factors that we're going to be using to predict a class, a category, whether an object or an observation belongs to class A, class B, or class C, have to be continuous. Okay. Now,
Teacher, can you repeat it again?
pardon me?
What needs to be continuous?
The predictors on the first method we're going to look, okay, only on this one, linear discriminant analysis. We'll go over the assumptions on each of the methods that we call, okay.
Thank you.
The only one that requires that the predictors are continuous are going to be this one, which is the linear discriminant analysis, and also quadratic discriminant analysis, which we'll talk about today, okay. These other methods that I listed here for classification do not require all the predictors to be continuous. Logistic regression, k-nearest neighbors, support vector machines, neural networks, and classification trees, those do not require that the predictors be all continuous or anything like that. So the first method we're going to talk about is perhaps the most limited and restrictive, but it's a very common method, or it used to be a very common method in the past. Now, classification problems occur in many different fields. I don't remember if we mentioned that why we can't use linear regression in a classification problem. Let's suppose that you want to predict a medical condition of a patient, okay, based on his or her symptoms. Now, let's assume that there's three possible diagnostics only. That patient has either a heart disease, heart attack, or an overdose, or an epileptic attack, okay? Those are the three possibilities. If we code the values as 1, 2, and 3, then we may say, well, I have a continuous response. So I have a variable that takes the values 1, 2, 3. It's a medical response. We could say 1 is if it's a heart attack, 2 is an overdose, and 3 if it's an epileptic attack. Now, the coding is arbitrary, right? And the coding here does not imply any order. This coding doesn't mean that a heart attack is, let's say, less serious than an overdose or less serious than an epileptic attack, because there's no natural ordering for the answers or the categories. Okay. So the coding can be arbitrary. I could have used another coding. I could use 3 to 1, okay, and it didn't matter because there's no particular ordering in these categories. There will be cases when there's an ordering, which is the case of a Likert scale, for example, but that can be treated as a continuous variable. Now, we'll be focusing in part because of ease of notation. It's going to be easier to talk about the different methods, assuming a binary response. But everything we do will apply to more than 2 categories. So, and the other reason to do this thing, not only in notation, but it's a problem that occurs very often in practice. We want to predict if it's fraud or not fraud. We want to predict if it's money laundering or not money laundering, if it is cancer or not cancer, or it's not cancer, and so on. So that's a very common case. Now, if there are only two possible outcomes, we can label them, for example, 0 or 1, or we could label them -1 and 1. Let's talk about this case only. I'm labeling at 0 if it is a heart attack, or 1 if it is an overdose. Okay, if I only have those possibilities as diagnosis for that. If we were to fit a linear regression model to this binary response and predict that the patient suffers from heart attack if y, let's say, is greater than 0.5, since I'm saying it's 0 if it's a heart attack and 1 if it's an overdose. So if I would say, I'm sorry, here, this is wrong. If I use this coding, then let me change the coding here. Just make a change in your notes. No, my escape does not work. Okay. I'm gonna do it, label it the other way around. Zero is going to be an overdose, and 1 is going to be a heart attack. This is going to be 1, and it's going to be 0. So that it's consistent with that what I say later. Okay. So if I code the variables like that, and I feed a regression model, then we could say, well, it's going to be a heart attack if y is greater than 0.5, because that's the middle point between 0 and 1. So if it's greater than 0.5, it's a heart attack. If it's less than or equal to 0.5, it's an overdose. Okay. It is not difficult to show that we would obtain exactly the same classification if we coded the variables the other way around, 0 and 1, the way I had it a little bit earlier. Okay. Now, it can also be shown that the estimate that we obtain from the linear regression model is in fact an estimate of the probability of the patient having a heart attack given the measurements of the predictor variables in X. Okay, and if that's the case, it's easy to show that the prediction could lie very well beyond 1 or lower. It could be also lower than 0, less than 0. Okay, imagine just a case where I have, let's suppose that I'm moving to a different case. It's 1 is cancer and 0 is benign, a benign tumor. Okay, suppose that's the categories there. Essentially, if we feed a really, and let's suppose that I'm going to make a graph here, and this is I'm going to change it to, instead of cancer, I'm going to make it something that makes more sense with the type of graph that I'm going to do here. And let's suppose that this is high blood pressure. That's not a good example. Let me make it here. Yeah, that's fine. High blood pressure. And suppose that X is equal to the weight of the individual. Okay. Then I have a sample of patients, and I have their weights, and some of them do not have high blood pressure. I should have changed this thing here. Blood pressure is okay. And some of them will have blood pressure that is okay. So I will get a bunch of zeros here. Okay. And some of them, I have 1. Some of them will be here. Okay. If I feed a regression line to this data, my regression would look like this. So that means that I will be able to predict that that the probability of having a high blood pressure is greater than 1 for some cases, right? For any weight greater than this number here, this prediction, this line that's predicting the probability of having high blood pressure given the weight of the individual will give me values greater than 1, and here to the left will give me values less than 0. And it's a probability, so it couldn't be like that. So using a linear model to model this type of variable, which is a binary response, is not a good idea. Okay.
Teacher,
Yes.
why did you change the values at the like 3 minutes ago if we would obtain the same classification? What was the purpose of changing those values, 1 and 0?
Here?
No, before you change in
Here?
yeah.
Oh, okay. Because in the statement I say, if we were to fit a linear regression model to this binary response and predict that the patient suffers from heart attack if y greater than 0.5, then y would be closer to 1 than to 0. Okay, so it would make sense to predict that it's a heart attack if it's closer to 1 than to 0.
Okay.
Okay, that's why, just to make it consistent with what I say here in the text.
Thank you.
Oh, you're welcome. Okay. Now, what is the general model in a classification problem, which is also, we'll use the term classification or prediction interchangeably, because there's a new patient, we want to classify it or predict if the patient will have a heart attack or not, okay? Or classify it as very likely to have a heart attack or not. So we'll use the term classification prediction interchangeably. Now, the relation, what we want to, the model that's behind this thing is we have a response Y, which is heart attack or not, or cancer or not, okay, in this case of the 2 categories. And we have a bunch of predictors, which we'll denote by P, a number of predictors. And the predictors could be, for example, if we're looking at this cancer, for example, could be age, gender, smoking or not, does the person smoke or not, and so on. Okay, so all these will be my predictor variables. And what I want to do is to find a function that relates these variables to my response, so that when I get another observation, another patient comes along, I can, based on these measurements, predict if that new patient is likely to have a heart attack or not, or likely to have cancer or not, or if that customer is likely to be committing fraud or not. So we need to estimate this function, okay? In machine learning or in statistical learning, instead of saying we're going to fit a function f to relate y with x, we say we're going to train a function f to predict y based on x. Okay, so we'll use the term train instead of fit, which is the term that we've been used to in statistics courses. Now, the precision of an estimate like f hat depends on 2 quantities. One is what we call reducible error. Reducible error is the error that we have that's attributable to the choice of the function f. Okay, that's the type of error that we can attribute to the choice of a function that we're going to estimate or train to predict y. And there's the irreducible error, and that's the error that exists even if we have a perfect estimator of the function f. Okay, that's the irreducible error. So the model y hat is equal to f of x plus some irreducible error epsilon. So some error epsilon, which has 2 components. So every model, there will be no model.
Professor, can you please go back to the previous slide?
Pardon me?
Can you please go back to the previous slide?
Sure.
Thank you.
Here I missed a hat here. Okay, y hat is f hat sum of x. Okay, but there's an error here. There is an error, and part of this error is going to be due to the choice of the function f, and the other part is going to be the irreducible error, which is the one that we would have even if we had a perfect estimate of f. Okay. So we'll if we knew what f is, and we'll see now a couple of examples. If we knew what f is, then I will still have an error, because there's the error inherent in there's no model that can give me a perfect prediction, let's say. Okay, no function, not even if I knew the right function, and we never know the right function, so we need to estimate it. And the different models that we are going to look at are different types of based on different types of functions to estimate this relationship between my response and the predictors. Okay? Are we okay so far?
Yes, thank you.
Okay. Now, how do we assess the quality of a function that predicts a response? That function f that we estimate. How do we assess the quality of a function that I train to predict whether a patient has cancer or not, or whether a transaction is a fraudulent transaction or not? In classification, the most common approach has been to measure the precision of an estimator through its classification error rate. Okay, what percentage of the time do I make mistakes classifying observations with that particular function? So let's denote by yi the category of the ith observation, and yi hat is the predicted or estimated category of the ith observation. Okay, so I have the true value and the predicted value. The error rate then becomes the average of this indicator function. So this indicator function will be 1 when yi different from yi hat. That is, when my prediction is different from the true, I add a 1. So that's the proportion of cases where I misclassified an observation. Okay. Because this is the indicator function, that's 1 if the response is different from my prediction, and 0 if the response is equal to the prediction. Now, of course, the error rate is also equal to 1 minus the percent of correct classification. Okay. If I call this thing the percent of correct classification, it's 1 minus that. So that's one of the natural ways to measure how good an estimate, a classifier is. Now, the base classifier is the classifier that minimizes the error rate over all possible classifiers. Okay. And this is the classifier that assigns each observation to the most likely category. If we have 2 categories, then that'll be the classifier that classifies each observation to belong as belonging to the class that has the highest probability of belonging. Okay. That is, we assign an observation represented by a vector x0 to the class J for which the probability that y equals little y, okay, that y is equal to what we observed, given x0 is the largest, okay? So we don't, you know, remember in this supervised learning context, we always have, let me make some space here. I have my observations, and my observation number 1, 2, 3, 4, up to n, okay? Now, each observation has a response. This is cancer, this is not, this is not, this is cancer, this is not, and so on. That's my response. And I also have p measurements, x1, x2, x3, up to xp, which are certain values of my variables. Maybe x1 is age, maybe x2 is weight, maybe x3 is gender, and so on, okay? So I have age, I have 35, 40, so on. 58. And x2 is weight, so I have either 70 kilos, 65 kilos, 58 kilos, and so on, 80 kilos. And x3 and so on. So we have all this data. So I have n observations there. The idea is I want to find the function that relates all these inputs to this response. So when a new patient comes here, that's the observation x0, that's a new patient. I don't know if that, I haven't done the analysis with that, to that patient. I haven't done the studies yet, but I have a patient that has certain age, certain weight, x0 p, and certain gender and so on. And when I want to be able to predict whether this patient is going to have cancer or not, okay? So what I want to do is estimate the probability that given these values, the new patient for whom I do not know the diagnosis yet, what is the probability that given those values, this patient will develop cancer or not develop cancer? Okay. So the Bayes classifier is the one that minimizes the error rate, and all it does is assigns each observation to a most likely category. Bayes classifier, we will never know what Bayes classifier is because we would have to know the true function f. To know Bayes classifier, we need to know f, and that's what we never know that. Okay, we want to estimate that. We want to train it. But we would Bayes classifier assigns, given that Bayes classifier knows what this function is, then this probability is known by the Bayes classifier, and it assigns the observation, the new observation x0, to the category for which this probability is greatest. So if I have 3 categories, it'll assign it to the category that has the largest probability, conditional probability given x0. Okay. Now, if we have k classes instead of only 2, we have k classes, we compute what's called the confusion matrix. And the confusion matrix has the actual class. See, when I'm training a model, I'm using data that for which I raised my drawing there. When I'm training a model, I'm using data for which I know the answer. I know if the patient has cancer or not. I know if that transaction was fraud or not. Okay. So I have the actual class that any observation belongs to. And for this data, where I do know what is the actual class, I predict which class it should belong according to the function that I am estimating. So I have a matrix that shows the actual versus the estimated class. It's called the confusion matrix. If you look at this matrix here, the elements in the diagonal tell me the observations that I classified correctly. The ones here in this corner, N11, are the observations that I classified as 1, I predicted as 1, and they actually belong to class 1. These here too in N22 are the observations that I predicted as 2 and are actually from class 2. So the elements in the diagonal are all the observations that I classified correctly. If I take the elements of the diagonal and divide it by total size of the sample, which is the sum of all these n's, that's the precision. Precision, which is also called percent of correct classification, okay, or accuracy. Several terms that I use for that, okay. So that's the percentage of classification, of correct classification. That's a confusion matrix, okay. Now, if we have a binary response, and we have only 2 possible answers, class 0 or class 1, a base classifier will predict class 1 if the probability that y is equal to 1, that is that the observation belongs to class 1, given x null, these values of, these are vectors, right, of dimension p. The probability that y equals 1 given x null is greater than 0.5. If I have 2 classes, the largest probability will be the one that's greater than 0.5. And that's what base classifier is going to predict. But base classifier needs to know this function, which is never known in practice. This is a graph that shows the conditional probability that y equals 1 given combinations of 2 variables. In this case, here p is equal to 2. I only have 2 predictors, okay? Weight, let's say this could be weight, and this could be height. And base classifier is this dotted line. The boundary that's drawn with this dotted line is base classifier. In this case, this data is simulated. They are simulated from 2 normal distributions. So we know what this probability is because we simulated the data, okay? We know what that is. And we can draw the base classifier. And the base classifier is the one that gives the smallest prediction error among all classifiers. Unfortunately, we never know it. We never know base classifier, okay? But we can simulate data to see how the base classifier looks like. Now, let me erase these things. So we mentioned already that base classifier produces the smallest error rate, which is known as the base error rate. So the smallest error rate in classification will correspond to the error rate that base classifier has. The error rate when x equals to x null is 1 minus the maximum over j. If we have more than 1 class, more than 2 classes, it will be 1 minus the maximum over all the different classes j of the probabilities that y belongs to j given x null. Okay, so if we have more than 2 classes, the error rate will be computed as 1 minus the maximum of these probabilities that y equals j given x equals x null. And in general, the what's called base error rate, it's an expected value. Base error rate is 1 minus the expected value of this maximum probability that y equals little j given x. So base error rate will be given by that. It's an expectation over all possible values of x for all the classes. Now, as I just mentioned, the operator expectation, the expectation operator, averages probabilities over all possible values of x. Okay. In the case of the data that I showed you, which is simulated data, this base error rate is 0.1304. That's base error rate, 0.1304. Base error rate is the analogous of the irreducible error, because to compute base error rate, we know what this probability is, what this probability distribution function is. And so it's the error, this error, base error rate represents the irreducible error. That is the error that we cannot reduce further because we're using the ideal function to predict. Okay. Now, of course, in theory, we would like to use always the base classifier, but for real data, we don't know what base classifier is. Now let's look at the confusion matrix when we have two classes. When we have two classes, the confusion matrix is the 2 by 2 matrix that has here the actual class and the predicted class. So N11 is the number of observations of it. To be able to estimate the model, we need to use data that for which we know the response. Okay, we call that training data. Okay, because we know the response. So to train the classifier, we use that this training data of all the data points in this training data set. The ones that the classifier classifies as 0, when the actual class is 0, are correct classifications, and so are the ones that the classifier predicts as class 1 and are actually from class 1. Okay. So from here, we have with this number here, N11, we call it the true negative. We normally use 0 and 1, and 1 will be the positive, 0 will be the negative. The traditional thing, the normal thing to do is, if we are interested in predicting fraud, then a transaction that's fraud would be coded as 1, and the transaction that's not fraud will be coded as 0. So the class of interest is the positive class. In the case of a particular type of illness, prostate cancer. Well, prostate cancer, if it's prostate cancer is 1, if it's not prostate cancer, it will be 0. Our target is to predict prostate cancer, and the positive class here is prostate cancer, because that's a class of interest. That's a class that we're interested in predicting. So we call this number here the true negative, because are the ones that are actually negative and I predicted as negative. So these are the true negative. These ones here, the N22, are the true positive, because I predicted them, the model predicted them as 1, that's positive, and they're actually positive. Okay. And this diagonal tells me the ones that were predicted correctly. Okay. Then when we have off the diagonal, we have N12 will be the false positive. Why false positive? Because I predicted them as positive and in fact are negative. So those are the false positive predictions. I predict them as positive and they are in fact negative. The ones in the lower diagonal are the false negative. False negative because I predicted them as negative, and they are really positive. So those will be false negative predictions. Okay. Now, there's some quantities that we compute from this confusion matrix. We compute sensibility. The sensibility is the true positive. Let me erase the same. For sensitivity, I take the true positive, which are these, and divide those by the total of true positive plus false negative. Divide those two by the sum of these two. Okay, that's the sensibility. Okay, that's the sensitivity. I put it. I wrote it down wrong here. It's sensitivity. Sensitivity. For some slides, I use the translator, and it's the common thing is to call this sensitivity. Sensitivity. Okay, and this is sensitivity. No. Sensitivity is not good. Okay. So sensitivity is the true positive observations divided by all the actual positive. This thing in the denominator, the true positive and plus the false negative, are actually the total of positives. So the sensitivity is a conditional measure. It's telling me the precision given that I have a positive case. So the sensitivity I can see this as a precision or correct classification given that the observation is positive, given that it's positive. Okay, that's the sensitivity. And the specificity is the true negative, which are these ones here, divided by the total of negatives. Okay, so there'll be the precision given that in terms of estimating the negatives, given that there is a negative. You may have heard the term specificity now that with the tests, the COVID tests, there were a lot of talk about, well, this test is not very specific. So the idea would be to have very high sensitivity and very high specificity. That will be the idea, because that will mean that the percentage of observations that I classify as positive, given that they are positive, is very high. And the percentage of observations that I classify as negative, given that they are negative, is very high. But these are conditional measures. And the precision is just the true negative plus the true positive over the total number of observations. Okay? Sensitivity is the true positive, yes?
What was the specificity? Like, the sensitivity tells me if the precision if the observation is true, but the specificity, I didn't.
Tells you the precision given that the observation is not true, that we have a false.
Okay.
That's why we say that those are conditional measures, because that's measuring the sensitivity measures how good your estimate is, given that you have given that the patient has cancer.
Okay.
The specificity measures how good the measure, the function, the classifier is to classify a patient as not having cancer, given that the patient does not have cancer.
Okay.
Okay.
Thank you.
Now, ideally, both should be close to 100. However, if sensitivity is very, very high, specificity is not going to be that high. Okay, if I want to increase sensitivity, I will sacrifice the specificity. Okay.
Okay.
So with sensitivity, we call it a true positive rate because that's the rate of true positives. Among all the positives, which are the ones that I'm signaling as true positives. And the false positive rate is 1 minus the specificity. That's the false positive rate. Okay. And there's a measure that combines both. It's very seldom used, but it's called the Young index, and it just sensitivity. I forgot to translate this thing. Sensitivity plus specificity minus 1. Okay, but this is not very commonly used. So we'll talk more about this sensitivity when we come back from the break. Let's take a break here. Kappa was developed to measure agreement in among different judges. Okay, for example, or different experts. So we have 2 experts, and there's one patient that one of the experts says this patient has illness type A, and the other expert says it has illness type B, for example, or either they agree on their assessment or they don't. So we have the same matrix here, the confusion matrix, where now I put here the marginals, the row marginals and the column marginals, okay, and the total is n dot dot. Okay, the Cohen's kappa is computed by the observed agreement. That is, the observed agreement is where both judges agreed, right? Or when the actual class agrees with the estimated class. So the observed agreement is N11 plus N22. The expected agreement is the product of the marginals. The product of the marginals is so you have N1 dot times N.1, this times this, plus N2 dot times N.2, this is the two marginals, divided by N dot dot for the total number of observations. Okay, so it's assuming that there's complete independence in the judgments of the judges or the experts. This would give you the expected agreement, given that there's complete independence among them, between them. Okay, the Cohen's kappa is estimated as observed agreement minus expected agreement divided by the total number of cases minus the expected agreement. That's the formula for Cohen's kappa. And it's such, I'm going to go here to an Excel file. See, for example, this is a case where both are in complete agreement. Okay, what we observed and what we forecasted are in complete agreement. So 15, forecasted 15 and observed 15 zeros, forecasted 10 ones, 10 positives, and got 10 positives. And my kappa is 1. Okay, I have complete agreement of both judges. In this case, they are not judges, they're complete agreement between the model, what the model predicts, and what the reality says. Now, if I reverse this thing, and if I put a 0 here, and a 15 here, and a 10 here, and 0 here, then I have complete disagreement, right? Complete disagreement between what the model says and what the observed data says. So the kappa belongs very close to -1. That's actually should be very close. Kappa is bounded between 1 and -1. Okay. And of course, when kappa is 1, we have complete agreement. Okay. If we have a mixture here, let's suppose that I have 50 here. I'm going to change it to 5 here. And then I'm going to leave that 10 there, and I'm going to make it 15. I'm going to reduce this thing a little bit. Okay. So I have some agreement, right? I have some agreement between the model and the observed, but I have some cases of disagreement, so it doesn't get to 1, but it's greater than 0.5. Kappa index is, you'll see it in the output of the software that we'll be using for most of the cases where we have to. Oh, I didn't record this thing. Let me go back in. Oh no, I'm still recording. I thought I was not recording. It's not very commonly used. I very seldom refer to the kappa index, because there's another way to look at this thing. In most cases, it's very clear the importance of sensitivity and specificity. And in fact, depending on the case, for example, let's suppose that I want to predict if a patient has a very severe type of cancer, okay, very severe type of cancer, and I have his or her clinical measurements. If I have a classifier, and that's a question for you, if I have a classifier that has sensitivity, classifier 1 has sensitivity 90% and specificity has 78%. And model 2 has sensitivity 85% and specificity, it has a specificity of about 80%. Now, my positive case here, 1 equals severe type of cancer. And you want to predict whether a new patient has a high probability of having this severe type of cancer. Which of the two models would you prefer? Model 1 or model 2?
Model 2?
Model
Yeah,
2?
I agree.
Yeah? Everybody agrees with model 2?
Yeah.
Okay. Well, it would be model 1. Because what is a most serious mistake? To have a patient tell him, you may have a very severe type of cancer, and I'm going to make you run some other tests. Okay. If he doesn't have cancer, what's going to happen? If he doesn't have that type of cancer, what's going to happen? He's just going to have to pay for more tests. But if I err on the other side, and if I tell him, no, you don't have, it's not likely that you have that type of cancer, then
He can die.
he can die, right?
Yeah.
So sensitivity is more important than sensibility, than specificity in cases like this. Okay. I could have also, see, for example, in this one, I could have let's say I'm going to change this thing to specificity of 90%, 95%. Okay. So what this means is that 85% of the cases who actually have that type of severe cancer, I'm going to tell them that they do have that cancer. Okay, I'm going to test them more. But here I have 90% of those patients I'm going to test. Okay, so I'm covering myself on the safe side. So I don't want to have somebody tell him that you don't have cancer when in fact he has that type of cancer. So sensitivity will be more important in that case. Okay. Is that clear why sensitivity is more important in that case?
Yes, teacher.
Okay.
But you also told me that it was important if the both of them were close to 100%.
Yeah, but you would have to with the one that has it's a 90 versus 95%. Okay, so it's only 5%, but it's only 5% that you may be saving the life. If those 5% that are in the difference, okay, you may be saving those lives.
Okay.
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 So 5% it seems to be important in that case. Of course, I could have made it more dramatic in the sense that the first model 1 was sensitivity of 98%, in model 2 sensitivity of 78%. Okay. Now, definitely, model 1 is preferable. Although specificity may not be that well, because specificity is not too high. For example, if I have a specificity here of, let's say that I have 45% specificity. If I have 45% specificity, that means that of the negative cases, I'm gonna predict them as negative 40%, 45% of the time. So I may have more people tested than required. Okay, but in that case, that's probably better because it just represents money and not a life. Okay.
Okay.
Now, there's the receiving operating curve. Okay, the receiving operating curve, this term comes from telecommunications. And that's a curve that was used by telecommunications engineers to measure the sensibility of a device in capturing a signal. Okay, so I send a signal, and it's a 1. And I want the receiving device to catch a 1. That's what it was called receiver operating characteristic curve. Is how well does the receiver operate? Okay. This is the most common method to combine sensitivity and specificity in a single value, which is the area under the ROC curve. Okay, this curve has an area under the curve, and now we'll see now that we want that area to be as close to 1 as possible. This is what I mentioned earlier. Sensitivity is conditional, is a conditional measure because it's a precision given that the event occurs, and specificity is a precision given that the event does not occur. Now, for certain, this is a built example. Okay. For certain set of credit data, sensitivity for an adjusted model, for model 1, let's say, was poor, 40%, while specificity was pretty good. Okay, this is for credit data. So I'm going to use this thing to see if I give a credit or not, or to detect a transaction as fraud or not, for example. So I have sensitivity of 40%. Specificity is pretty good. Okay. Now, the positive case is that the customer will default. That's a positive case. 1 is the customer will default, and 0 is the customer will not default and will pay on time and so on. Now, these values are computed using the cutoff point that by default most classifiers use, which is 0.5. So if the probability that I estimate for the customer to default is greater than 0.5, I classify it as default. And if it's less than or equal to 0.5, then I classify it as non-default. And I give him the loan, or give her the loan. So this is assuming the cutoff point of 50%. The ROC curve, ROC curve, looks like something like this. We draw in the x-axis, we have 1 minus the specificity, okay? 1 minus the specificity. Remember that the specificity is the precision given that the event does not occur. So the specificity of 0 give me a value of 1 here in this curve, right? A specificity of 0. And since in the y-axis, we have the sensitivity, okay? So a perfect classifier would be something that is like this. The perfect classifier. I'm going to build a perfect classifier. That's a perfect classifier. Okay, that is a perfect classifier because it sensitivity is highest and specificity is highest, is at 1. Okay, so the area under this curve is 1. Okay, the area under this curve is 1. Now here we have 2 cases. First, let's talk about how this ROC curve is built. The way we build ROC curves is as follows. We pick different cutoff points. Okay, we play with the cutoff points. So we choose a cutoff point of 0.1, a point of 0.05, 0.1, 0.15, and so on. So I use different these are different cutoff points. For every cutoff point, I compute the confusion matrix for that classifier. Because every cutoff point will give me a different confusion matrix. Because I will be assigning as 0s or 1s, depending on that cutoff point, for the probability of belonging to one of the 2 classes. So for every different value of a cutoff point, I have a sensitivity and I have a 1 minus a specificity. And that I do that for all possible cutoff points in the range between 0 and 1, right? So all these correspond to different cutoff points. This one here is the one that corresponds to a cutoff point of 0.5. With this cutoff point, 0.5, I get a specificity of 0.92. So that's 1 minus specificity is going to be 0.08, 0.07, right? Which is around here. That's here. And sensitivity is 0.4. Here's sensitivity. Now, if I lower the cutoff point, see what happens. If I lower the cutoff point, then I'm essentially making it easier to classify something as a 1, as a positive, than a negative. So if I decrease it to 0.3, my cutoff point, my specificity increases to 0.78, and sensitivity increases by my specificity decreases from 0.92 to 0.78, and sensitivity increases from 0.4 to 0.6. Okay. So if I prefer to have higher sensitivity, then I need to lower the cutoff point for that classifier. Okay. Give you an example of a project that we did with one bank in Mexico. If we'd used the cutoff point of 0.5, our sensibility was very poor, was very, very poor. And that had to do with money laundering. So if you fail to report a transaction, if a bank fails to report a transaction as an unusual transaction, non-usual transaction, suspect of money laundering, the fines can be huge. And I don't know if you remember a case with HBC a few years ago where the fines were really, really high, in the thousands of, no, millions, more than $100 million, something like that was the fine, because they did fail to report the transaction. So the cutoff point that we are using in that model to alert a transaction as possible possible money laundering, the cutoff point is 0.95. That's the cutoff point. Okay, so we could increase the sensitivity. Now, and what it says here is what we saw in the graph. If we lower the cutoff point to 30%, the model sensitivity improves to 60%. Okay, but specificity decreases. There's always a trade-off between specificity and sensitivity, and of course, the ideal classifier will be one that behaves like which ROC curve looks like the red lines there, but that's very difficult to achieve. So, but the area under the curve, you compute the area under the curve of this rectangle, that will be 1, and here the area under the curve of this classifier, if you look at the area under the curve here, it should be around what, probably 0.75 or something like that, maybe 0.75. This line that you see here, this line, the diagonal line that you see here, this 45-degree line, if a classifier gives a narrow C curve like that, that classifier works exactly the same as if you were tossing a coin and deciding whether, if it's heads, I classify it as A, if it's tails, I classify it as B. Okay. That's the area under this curve. The area under this curve here is 0.5. 0.5. So that's the ROC curve has several advantages. One of the advantages that it has is that if I have classes that are very, very unbalanced. What do I mean by an unbalanced class? Let me talk a little bit about the case. I'll go with this white spice here, this light. That's in blank. See, in the money laundry case, we have 0.0 less than 0.03% of transactions were what's called unusual. That is, these are transactions that need to be investigated to see if they report them to the regulator. When you have this type of behavior, the classes are very unbalanced, are extremely unbalanced. I have very, very few transactions that are money laundering, very few. And most of my transactions, 99.97% of my transactions are not money laundering. When we have that that big of an imbalance, then using the correct classification is not a good criteria to select a model. look at the case where I have, suppose that class in the population, my ones, which is the class of interest, represent 99% of all the cases. Okay, then I can have a classifier with a 99% correct classification. If I classify all as zeros, right? If I classify all observations as zeros, then I have a classifier that's a 99% correct classification. So correct classification would not be a good criteria here. And the criteria we use with unbalanced classes is normally the ROC curve. Okay, normally. There's other criteria. Okay, there's a criteria that says equate sensitivity with specificity. That's another criteria. But the most common is the area under the ROC curve. Okay, this is what I explained, how the ROC curve is built with computing sensitivity and one minus specificity for the different cutoff points. And it is used as a measure of the quality, the predictive quality of a classifier. And this is very important. Another advantage is that it is insensitive to class imbalance. Okay, here it doesn't matter if I have a very high imbalance in my classes. There have been efforts to extend the ROC curve to more than 2 classes. However, these efforts have some flaws. None of the methods that have been developed to extend the ROC curve to more than 2 classes has worked as well as required to be a common method to be used. So raw curve is normally used with 2 classes. Okay. So those we now know which criteria we're going to be using to evaluate different methods. Okay. Now let's look at the simplest discriminant function or classifier that was one of the first ones developed many years ago, and then it's related also to what's called Fisher's linear classifier. We'll see what's the relationship. Now, there's primarily 2 objectives in analyzing the separation between groups. One is the description of separation. Okay, so we want to describe how these classes are separated. Okay, which variables contribute more to separate the 2 sets of variables. With the example of the Swiss bank notes, we saw, for example, that the diagonal measurement is a variable that has a huge impact in separating the legal notes versus the illegal notes, the counterfeit. Okay. The other one is prediction or classification, which is the main objective, the main focus in this class is prediction or classification. Now, the first method, one of the first methods developed was using a linear function of the p-predictors to assign a new observation to one of the groups. However, we saw that linear regression doesn't work because the response is categorical. So we'll see how the linear discriminant analysis was developed. Let's suppose that we have G groups, okay? And we have K groups, K capital Case groups, and let's denote by G equal to the group for which an observation belongs to. So G equals 1, or 2, or 3, up to K. If we have 2 groups, if K equal to 2, then G equal 1 could be prostate cancer, and G equals 0 no prostate cancer. Okay, that's the Y that we were using earlier. Now, each observation consists of P factors. Okay, and we'll denote by X. We know that X is a vector observation that has P variables. It could be height. In the case of the Swiss bank notes, what the variables were diagonal, the diagonal measure, bottom and left height, right height, bottom to lower, bottom top to inner, and so on. Okay, so there was the measurements of these nodes. Those were in that case we have 6P equal to 6. Now we know that Bayes classifier is optimal, and then what we would like to know is if an observation, a new observation X, belongs to class lowercase k. Okay, is J equal to little k or not? So what we need to know is what is the probability of J equals 1 or 2 or 3 up to k, given my predictors, given my P predictors, X1 through XP. Let's denote by pi sub k the prior probability of a class K. Okay. In some cases, we usually don't know the prior probability, but we can estimate it. Okay, we estimate the prior probability. But let P sub k the prior probability of class K. Okay. For example, if I know there are some cases, for example, with certain illnesses, in which the medical professionals know what's the prevalence of that illness in the population. Okay, for example, they know what the prevalence of breast cancer in certain population, the US, for example, or in Mexico, and that we can use that prevalence as a prior probability that a patient has cancer, for example, breast cancer. Since we have K capital K case classes, the sum of these prior probabilities will be equal to 1. That is, an observation will belong to one and only one of the classes, and all the classes are exhaustive. Okay, an observation belongs to one and only one of the classes, and all classes cover my whole population. I don't have any class that I don't know that I'm not considering. Now let's note by f sub k of x the PDF of x of this p predictor. So this is a multivariate distribution density function, p variate, because we have p variables, and that's the PDF of x in class j equal to k. That's what the subindex sub k. So this is the PDF, the joint PDF of x in class little k. If you remember your Bayes theorem says that the probability that my observation with these values of x belongs to class k, class little k, given all those values of the p variables, is going to be the k, the density function for the for that class, for x in that class, okay, times the prior probability of that class divided by the sum of all the joint densities for the k classes, each one multiplied by its prior probability. Okay, that's Bayes theorem. That is Bayes theorem. Now, the key then is to estimate this. We need to estimate the densities. To estimate this probability, because we don't know it, we need to estimate all the densities. So we need estimates of its densities. Okay. Now, there are different models that have been developed around this formula based on Bayes' theorem. Okay. One alternative would be to build a non-parametric estimate of f, right? We could build non-parametric estimates of f. That's one alternative. Kernel estimates of the function, of the joint density functions. The two methods that we're going to see here are linear and quadratic discriminant analysis. And they are based on using Gaussian densities for f. Okay, so both this linear and the quadratic discriminant analysis are based on assuming that the joint density function for the p variables is multivariate normal. And the other the other method that we will study is called naive Bayes. And naive Bayes has is a method that has something that we will be calling hyperparameters, and one of the hyperparameters is which densities we use to compute this classifier. We'll talk about this method later. We'll focus now on the linear and the quadratic discriminant analysis. First, the linear discriminant analysis. Okay. Now, under the assumption that the joint density function for the p variables is a Gaussian distribution, is a normal density function by p-variate normal density function. The density function is going to be given by one. We saw this thing when we talked about the multivariate normal distribution, is 1 over 2 pi times raised to the power p over 2, where p is the dimension of this multivariate normal. Sigma sub k, the determinant of sigma sub k, where sigma sub k is going to be the variance covariance matrix of x in the kth group. Okay, in the kth group, this will be the variance covariance matrix times the exponential of -1/2 x minus mu sub k is the mean in the kth group, transpose times sigma sub k inverse, which is the variance covariance matrix in the kth group, x minus mu sub k. That'll be the kth joint density function for the p variables. Now let's look at the linear discriminant analysis. In the linear discriminant analysis case, we're going to assume that these matrices, the sigma sub k's, are the same in every group. That is, I have in all the groups, we have that sigma sub k is equal to some variance covariance matrix sigma. That is, we have the same variance covariance matrix in all the groups. When we compare two classes, K and J, let's say, K is lowercase k and small j, lowercase j, all we have to do then is to look at the log likelihood. If we look at the log likelihood of the probability that G equals K given my values of X, divided the probability that G is equal to J. That is, what is the probability? This is the distribution that the probability that G, the observation belongs to the kth group, divided by probability of observation belongs to the jth group, given my vector of P predictors or factors. So that will be just the logarithm of the f sub k divided by fj, plus the log of pi sub k divided by pi sub j. Okay, remember, these are the prior probabilities of the kth class and the jth class. And that is equal to the log of pi k over pi j minus 1/2. When I take this ratio and take the logarithm, I get minus 1/2 of x mu minus 1/2 mu sub k, the mean of the kth group, minus the mean of the J group transpose times sigma inverse, because I have a common variance covariance matrix, times mu sub k minus mu sub j, plus X transpose sigma inverse X k mu j minus mu k. Okay. Now, if you look at this expression here, there's no X involved here, right? I have X involved here. I have X here, but it's just the transpose of X multiplying this sigma inverse times mu k minus mu j. Okay, so this is, of course, if you look at, focus on this piece, this is a linear combination of the X's. Okay, so this whole thing is linear in X. And is going to yield a p-dimensional hyperplane. Okay, is it clear why this is a linear combination of what this thing is linear in X? I guess it's clear because nobody said anything. So
Yes, teacher, it's
okay,
clear.
good.
I think so.
Okay, so it's linear. That's why it's called linear discriminant analysis, because that the discriminant function is going to be linear in X. Okay, and that is true for any pair of classes. That is, if you have 4 classes, any pair will satisfy this relationship. Okay, there will be the function that separates each pair of groups, each pair of classes, is going to be linear function in X. So the decision boundaries are linear. The decision boundaries are going to be linear. Okay. From this equation that we have here, we just write down what the decision boundary is going to be, what's the discriminant function, and the discriminant function for group K, little k, is going to be X transpose sigma inverse mu k minus 1/2 mu transpose sigma inverse mu k plus log of pi to k. That's it. That's going to be the discriminant function. And using this function will be equivalent to the decision rule that says that g of x is going to be the one that maximizes over the different k's. I'm maximizing over k delta sub k of x. So for the different classes, compute delta sub k of x, and the predicted group is going to be the one that maximizes this thing here. Okay. Now this is just we don't know the parameters of the Gaussian distribution nor the prior probabilities, so we estimate them. We estimate the prior probabilities with the number of observations from the kth group divided by n. We estimate the mean using the sample mean of the kth group, and we estimate the variance covariance matrix sigma as the pooled version of the different variance covariance matrices that we have. We have each class has its sample variance covariance matrices, and they are not the same. So we average them to construct a pooled version of the variance covariance matrix, since the assumption is that all of them are equal. That is the assumption. Okay. Okay, let's see. It's 15 to 12. Let's stop here.